You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. A sound monitoring strategy is essential for keeping cloud services both reliable and secure. The purpose of monitoring is not only to detect outages, but to continuously evaluate performance, stability, and potential risks through structured observation. In modern environments, this means unifying three main forms of telemetry: metrics, logs, and traces. Metrics quantify system health numerically over time. Logs record discrete events that explain what happened and when. Traces follow requests through distributed services, providing end-to-end visibility. By combining these perspectives, organizations gain actionable insight into how systems behave under real workloads. This unified approach enables faster diagnoses, clearer accountability, and greater confidence that services meet reliability and security expectations. Monitoring in the cloud is ultimately about turning data into understanding, and understanding into dependable action. Monitoring itself is the continuous observation of system behavior. Unlike one-time tests or static configurations, monitoring provides an ongoing assessment of health, performance, and risk. It watches how applications, infrastructure, and users interact in real time, surfacing deviations from expected behavior. For example, sudden spikes in CPU usage or unusual login attempts are captured and reported. Monitoring makes systems transparent, turning invisible operations into observable patterns. By observing continuously, teams can respond to emerging issues before they escalate into outages or compromises, maintaining trust in the services provided. Observability goes beyond monitoring to describe a system's ability to reveal its internal state through external outputs. A highly observable system emits sufficient telemetry metrics, logs, and traces that engineers can infer what is happening without direct access to internal components. For example, if a microservice is overloaded, observability ensures that latency, error logs, and traces across upstream services clearly indicate the cause. This concept is critical in cloud-native environments where systems are distributed and opaque. Observability ensures that the right signals exist to answer the hard questions operators will inevitably face. Metrics form one of the foundational pillars of monitoring. They are numeric time series that quantify service performance across dimensions such as rates, errors, latency, and resource saturation. For instance, tracking requests per second, error percentages, or memory utilization provides insight into service health. Metrics are efficient to collect and store, making them well-suited for real-time dashboards and alerting. However, they provide context only at a high level, requiring logs and traces for detailed root cause analysis. Metrics serve as the early warning indicators that highlight when something may be going wrong. Logs add detail and narrative to the picture. They are time-stamped events that describe specific actions or states, such as a user authentication, an error message, or a system configuration change. Logs are invaluable for forensic investigation because they provide the context and sequence of actions leading to an event. For example, a log might show the exact query that caused a database error. Because they can grow in volume quickly, logs require disciplined management, including indexing, retention, and redaction policies. Properly handled, logs complement metrics by explaining not just that something happened, but what exactly occurred. Traces provide the third dimension by following a single request across multiple services. They use spans to represent operations and record timing, dependencies, and outcomes at each step. In a distributed cloud system, a trace might show how an API call travels from a front-end gateway through authentication, service layers, and database queries. By correlating timing and path, traces reveal bottlenecks or failures that metrics and logs alone cannot. Tracing transforms a system from a black box into a flow diagram, showing how work is executed across components and where inefficiencies or vulnerabilities lie. The golden signals of latency, traffic, errors, and saturation form a concise framework for monitoring reliability. Latency measures how long operations take. Traffic gauges demand on the system. Errors reflect failure rates, whether user-facing or internal. Saturation describes resource consumption relative to capacity. By focusing on these four signals, teams capture the essentials of service health without drowning in data. For example, rising latency combined with high saturation often signals resource exhaustion. The golden signals provide a shared language for diagnosing issues quickly. Service level indicators, or SLIs, transform these raw signals into user-centric metrics. An SLI is a precise measurement of behavior that matters directly to users, such as the percentage of requests completed within 1 second. SLIs shift the focus from internal metrics to external outcomes. For example, CPU utilization is important to engineers, but what users care about is how fast their requests are processed. By tying SLIs to user experience, organizations ensure that monitoring aligns with real reliability goals. Service level objectives, or SLOs, set target ranges for SLIs and guide operational priorities. For instance, an SLO might state that 99.9% of API requests must succeed within 2 seconds. These objectives define what acceptable reliability looks like and drive alert thresholds. When performance drifts below SLOs, it signals the need for intervention. SLOs create a contract between engineering and business, ensuring that reliability is measurable, intentional, and aligned with user expectations. They help teams prioritize fixes that matter most to customers. Time synchronization is a subtle but crucial enabler of monitoring. Without accurate clocks, logs and metrics cannot be correlated reliably. Network Time Protocol, or NTP, ensures that events across systems share consistent timestamps. For example, if a trace shows a request spanning 2 services, synchronized clocks ensure that the order of events is preserved. Inaccurate time creates confusion during investigations and undermines evidence credibility. Time synchronization is therefore a foundational requirement for dependable observability. Schema standards and normalization align telemetry fields so that data can be correlated across services and providers. For example, normalizing terms like error code versus status code ensures that queries span multiple logs seamlessly. Without standardization, each service may emit slightly different formats, making analysis brittle and fragmented. Normalization allows metrics, logs, and traces to be stitched together coherently, producing holistic views of system behavior. In multi-cloud environments, schema alignment is indispensable for unified monitoring. Correlation identifiers further strengthen this coherence. Request IDs, trace IDs, or session tokens link data across telemetry sources. For example, a trace ID may appear in logs, metrics, and span data, allowing investigators to follow a single request end-to-end. These identifiers act like thread stitches, weaving together disparate signals into a single narrative. Without them, telemetry remains fragmented, and root cause analysis becomes guesswork. Correlation IDs turn a sea of data into connected stories. Because telemetry can be overwhelming in volume, sampling and aggregation balance fidelity with cost. Sampling selects representative subsets of data, while aggregation summarizes trends into averages, percentiles, or counts. For example, storing every trace may be prohibitively expensive, but sampling 1% of traffic provides insight without overload. Similarly, aggregating latency into percentiles highlights tail performance without retaining every individual request. These techniques ensure that monitoring systems remain sustainable at scale. Cardinality management further ensures that time series databases are not overwhelmed by overly complex labeled dimensions. For example, recording metrics with user IDs as labels creates unbounded cardinality, quickly exhausting storage and query capacity. Instead, dimensions must be scoped to meaningful groupings, such as service or region. Cardinality discipline preserves the efficiency of metric systems while still capturing the patterns that matter. It prevents telemetry from collapsing under its own weight. Privacy by design logging ensures that telemetry itself does not become a liability. Logs must minimize sensitive content, redact personal data at the source, and restrict access appropriately. For example, an authentication log should record a user's login attempt, but never their plaintext password. By designing logging practices with privacy in mind, organizations reduce compliance risk and protect user trust. Observability must illuminate system behavior without exposing sensitive details unnecessarily. Coverage planning rounds out monitoring strategy by identifying mandatory telemetry across control plane, data plane, and application tiers. For example, control plane events might include configuration changes, while data plane telemetry covers request handling, and application telemetry records business logic. By defining mandatory coverage, organizations ensure that monitoring is complete and not biased toward only certain layers. Comprehensive coverage prevents blind spots and guarantees that no critical area of the system operates without visibility. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Collection models form the backbone of how telemetry is gathered from cloud services. Agent-based collection involves deploying software agents on hosts or containers to forward metrics, logs, and traces. This offers deep visibility, but requires maintenance of the agents themselves. Agentless collection relies on provider APIs and services to export telemetry, reducing operational overhead but sometimes limiting detail. Provider-native exports strike a balance, using built-in tools such as CloudWatch, Stackdriver, or Azure Monitor to provide signals without extra infrastructure. Each model carries trade-offs in depth, cost, and management effort. Choosing the right approach often means blending these models to achieve comprehensive coverage. Another key design decision is whether to use push or pull patterns for telemetry delivery. In push models, agents or services send data proactively to collectors, ensuring low-latency updates but raising risks of backpressure if receivers are overloaded. In pull models, collectors request data from exporters at intervals, providing flow control and firewall simplicity but with potential lag. For example, Prometheus typically uses a pull model, while Fluentd relies on push. The choice depends on workload sensitivity to latency, infrastructure topology, and tolerance for network constraints. Both approaches can coexist in hybrid architectures. Centralized aggregation and federated observability represent two competing organizational patterns. Centralized systems ingest all telemetry into a single platform, simplifying correlation but creating a larger blast radius if compromised. Federated observability, by contrast, keeps data within local domains, offering autonomy and resilience but requiring cross-domain queries for global insight. For instance, a large enterprise might centralize metrics in a corporate data lake while allowing business units to maintain local observability stacks. Balancing central control with federated independence is essential for both scale and security. Alert design determines whether monitoring helps or hinders. Poorly tuned alerts overwhelm operators, while well-designed alerts highlight only user-impacting symptoms. For example, alerting directly on high CPU usage may generate noise, whereas alerting on user-visible latency ensures relevance. Symptom-focused alerts reduce fatigue and build trust in monitoring systems. They also help operators prioritize interventions based on customer experience, not just system internals. Alert design is thus both technical and human-centered, balancing sensitivity with clarity. Runbooks translate alerts into concrete action. Each alert should have a corresponding runbook that encodes diagnostics, mitigations, and escalation steps. For example, a database connection errors alert might guide operators to check connection pool saturation, review recent deployments, and escalate to the database team if unresolved within 30 minutes. Runbooks reduce response variability, accelerate recovery, and make even junior staff effective under stress. Encoding these steps into automation platforms makes them executable at machine speed. Runbooks bring discipline and repeatability to incident response. Anomaly detection strengthens monitoring by going beyond static thresholds. Seasonality and baseline-aware models can distinguish between expected variations and genuine issues. For example, traffic spikes during peak business hours may be normal, while a similar spike at midnight signals trouble. Machine learning or statistical models adapt to historical patterns, reducing false positives. By complementing threshold alerts with anomaly detection, teams capture both predictable and unpredictable risks. This dual approach increases confidence in the signals provided by telemetry. Dashboards transform telemetry into role-specific views. Operations teams may focus on system availability, engineers on performance bottlenecks, and security analysts on suspicious events. Well-designed dashboards highlight relevant SLIs, error budgets, and trends, while also offering drill down into details. For instance, a dashboard may show high-level uptime metrics while linking to detailed traces for root cause analysis. Dashboards make observability accessible across roles, ensuring that data is not siloed but shared as a common language of reliability and security. Dependency maps and service graphs enrich telemetry by showing how components relate. Metrics, logs, and traces become more meaningful when contextualized with upstream and downstream links. For example, if a payment service fails, a dependency graph can show which checkout workflows are affected. This context accelerates troubleshooting and prevents teams from chasing symptoms in isolation. Service graphs also highlight hidden dependencies, such as external APIs, which may be overlooked until they cause cascading failures. Visualizing these links ensures that telemetry supports both diagnosis and design improvement. Cost governance is increasingly critical as telemetry pipelines grow in volume. Tracking ingest rates, retention tiers, and query patterns ensures that observability remains affordable. For instance, hot storage may be reserved for recent, high-value logs, while long-term retention uses cheaper cold storage. Monitoring budgets align costs with business priorities, preventing runaway expenses. Cost governance also encourages efficient telemetry, reducing waste from redundant or noisy signals. By treating observability as a resource to be managed, organizations preserve both safety and sustainability. High availability for telemetry pipelines ensures that monitoring itself does not become a single point of failure. Techniques include replication of collectors, retry mechanisms for exporters, and dead letter queues for events that cannot be delivered immediately. For example, logs may be written to a local buffer if the central collector is temporarily unavailable. Ensuring telemetry pipelines are resilient guarantees that evidence is captured even under stress, such as during outages or attacks. High availability turns monitoring into a dependable safety net rather than an unreliable afterthought. Testability ensures that telemetry signals and alerts can be trusted. Synthetic probes simulate user actions. Canary checks test specific routes, and chaos experiments stress systems to validate whether signals trigger appropriately. For instance, intentionally taking down a service can confirm that monitoring detects and alerts correctly. Without testing, monitoring may provide false assurance, missing issues until they are real. Testability builds confidence that observability systems work as intended, not just in theory but in practice. Multi-cloud normalization addresses the challenge of working across providers. Each cloud may define severity levels, metric units, or log formats differently. Normalization harmonizes these into common schemas so that dashboards, alerts, and reports remain portable. For example, CPU utilization may be expressed differently across AWS, Azure, and GCP, but normalization ensures they align for comparison. This allows organizations to monitor hybrid and multi-cloud systems as a cohesive whole, reducing complexity and strengthening governance. Evidence generation from telemetry turns monitoring into an auditable practice. Logs can be signed, Metrics can include integrity proofs, and alert outcomes can be packaged as compliance artifacts. For example, an audit may require proof that all administrative logins are logged and retained for 1 year. Evidence generation ensures that telemetry supports not only operational recovery but also regulatory assurance. It transforms observability from an operational tool into a governance asset. Access governance enforces least privilege in monitoring systems themselves. Reading logs, administering dashboards, and mutating alert rules should be scoped to roles with legitimate need. For example, developers may have read-only access to application logs but no rights to alter alert thresholds. Access controls prevent tampering and reduce insider risk, ensuring that observability systems themselves remain trustworthy. Governance of telemetry access recognizes that monitoring data is sensitive and must be protected like any other critical asset. Continuous improvement keeps monitoring strategies aligned with evolving realities. Reviews of false positives, misdetections, and postmortems identify gaps and inefficiencies. For example, an incident may reveal that trace coverage was insufficient or that an alert threshold was too lenient. Incorporating these lessons refines signals, dashboards, and runbooks over time. Continuous improvement ensures that monitoring systems adapt alongside applications and threats, preventing stagnation. It turns observability into a living discipline, always learning and adjusting. In summary, disciplined metrics, logs, and traces aligned to service-level objectives create actionable visibility for dependable cloud operations. Collection models, delivery patterns, and normalization provide coverage across providers. Alerts, dashboards, and anomaly detection ensure that signals are meaningful. Cost governance, access control, and evidence generation ensure sustainability and compliance. Finally, continuous improvement ensures that monitoring evolves as systems and risks change. Together, these practices transform telemetry into trust, enabling organizations to maintain reliability and security in complex cloud environments. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.